Hello, everyone, and welcome once again to Cave to the Cross Apologetics. I'm Patrick.
And I'm Tony.
And in our series here, we're inviting you along for our book study that we're doing together. And we just kind of take a book on philosophy or theology and kind of go one chapter at a time and kind of break it down so that you may also enjoy what the world of philosophy has to offer, and also we look at things like worldview and just different ways that people try and knock down the Christian faith and how best to defend it. So this can be for unbelievers as well as believers. So hopefully we are a good service to you, and so we ask that you like the videos or the podcast, that you leave comments on iTunes if you go there, or you subscribe through whatever podcast amalgamation that you do for all your podcast needs, or even on YouTube where we do the videos for these. And also we cut the videos into segmented parts so that you're able to share them or just digest them in smaller bits and chunks. So if you share those on Facebook or on YouTube, we'd be happy with that as well.
So today we're going to continue our discussion in Cave to the Cross Apologetics on Mitch Stokes' book, How to Be an Atheist.
Yes.
Right?
So we are not trying to be atheists, but if we were to be atheists, this is how to be the best atheist. So
that's right.
He invites us, both atheists and believers, to be sober skeptics so that we aren't just believing everything quickly, but we're also not dismissing everything quickly. And one of those things that we're not believing or dismissing is whether or not science is atheistic in nature, and whether or not it explains or disavows God.
Yeah. So this chapter, we're worked our way to chapter 6. Last time we talked about chapter 5 was titled Photoshopped Science, and we saw that the logical positivist, Stokes tells us, had a picture of science that turned out to be heavily doctored, he tells us, right? Their Photoshop version was pristine and pure. Excuse me. In fact, he says it was a little too perfect, eerily smooth, and plastic-like. Up close, it didn't look human, right? And so in chapter 6 now, he wants us to be aware, and so he's going to defend the idea that real science is hard. Right? Real science is hard. And so so he starts off this chapter by talking about credulity, he says, is a cardinal sin for skeptics, right?
Believing things easily is not what we want in skeptics. In fact, that's the opposite of what skeptics want.
That's right. So we don't want to be gullible.
You are not a good skeptic if you believe everything quickly.
Right? And so he says the idea here, the idea that eventually he's going to get at is anyone today who believes in God and uses cell phones and computers, he tells us, is wholly culpable. You can't have it both ways. Science has, and here's the issue that he eventually wants to get to, science has proven itself trustworthy as evidenced by its astounding and astonishing technological gifts.
Right.
It works, and therefore we should believe what it says. And what it says many folks, right? And he gives us an example here, or at least strongly suggests, is that there's no God. That is, science implies naturalism, right? Naturalism is the idea that nature is all there is. There is no supernatural. And so if nature is all there is and there is no supernatural, then there's no supernatural God.
Right.
Yeah. And so in the next few chapters, he tells us, I want to argue that we should be somewhat skeptical of what science says, notice this, about the fundamentals of physical reality. Now, that's what science is all about, explaining and talking to us about the fundamentals of physical reality. And so he's going to suggest that we should have sober skepticism about what science says about the fundamentals of physical reality, right? Which is kind of an interesting claim.
Right. In the last chapter, we did talk about that Photoshop science, and that people, like the logical positivists, brought along this idea that they got rid of the junk and they whitewashed it and made it clean and logical and as Spockian as you could get it. But there are fundamentals of human nature where we're utilizing a system that is that when you bring humans into the equation, it kind of garbles a lot of things up. And so that's what this chapter kind of critiques, is that robotic scientist in the lab titrating, measuring.
They have to have white coats.
Yeah, of course. Of course, you're not a scientist without it. It's like a doctor with a stethoscope. Always has to have it. So we want to look at actually not it's not really a critique of science per se, but of what people claim science is, and also how to get especially at things like the theory. How do you establish a theory? What does a theory look like? It's not something that just arises out of the ether. It's something that people bring about, and so there are pros and cons to having people involved in science.
Yeah. So what he tells us is, I'll describe some important ways in which the scientific method is much more complicated than what we often think it is, right? So that's it. So he starts off with this, with what you just suggested here is a theory, right? The idea of theory. It's just a theory is the thing here,
which
right?
many Christians have on Facebook have thrown out at the atheist who wants to say evolution did it. Oh, it's just a theory. Evolution is just a theory.
Exactly.
Yeah.
So if indeed, so that's what he says here. He says, what makes a scientific theory? A lot of confusion, he says, could be avoided if it were dealt with up front. A good example is what you just said, the idea that someone objects to evolution by pointing out that it's only a theory. Right?
Well, gravity is just a theory, too.
Right. The objection seems to be that we need not believe it because it's just a theory. In other words, if it's just a theory, then it's less credible. It may not be supported by good evidence, and so we need to hold it tentatively, right?
Again, I think this is a downfall of at least the Western education system, because they drill into your head theory, hypothesis, experimentation with observation, and then conclusion. And that's the way it's always been. And you get higher up in the educational sphere, and you realize that hypothesis is can't be diverted away from theory, because what it's not just an educated guess. It's more than that, because you're just educating guessing. You can come up with anything.
That's right.
But you need to establish a good, coherent, logical theory that has different elements that we'll see later on too.
So lack of certainty is not what makes evolution a theory, he says. Evolution, of course, is a theory, and it's clearly, he says, it falls short of certainty, but that itself is no condemnation. All theories suffer from the affliction of lack of certainty to a certain degree, right? And so rather, the main feature of a scientific theory, and now he gets into our definitions here, right? So he says the main feature of a scientific theory, what makes it a theory, is that it is inferred rather than observed. So it's inferred rather than observed. No one has ever seen a theory by definition.
Right. So think back a couple chapters ago when we talked about the billiard balls. No one actually sees what causes the striking. No one sees what that transfer of energy is. There's a cause and an effect, and we don't see the in between to it.
Right.
So the why is inferred. The what happened is observed.
Right.
Yeah.
Right. Yeah. So good. So so then he wants to help us to understand this. He says the observation theory distinction falls right along the sense perception reason divide, right? So you have observation and you come up with a theory, and he says it's real similar to the sense perception and reason, right? That those same type of divides.
Hume's fork that we saw
Right.
two episodes ago,
Right.
where those are the only means by which a naturalist can come about with knowledge. Is it's either observed with our senses, and that's it,
Right.
or it's it's come about through logical means or definitional or mathematical.
Right. Right. Yeah. Good. So so he gives us an example here to help us to see. He says, imagine that you're outside in the rain, right? You get to his office. So you directly observe that it's raining, right? It's raining, you see it, you're being rained upon, that sort of thing, right? And then you get to, and so that's a direct observation. And so there's no necessarily, I mean, there's some assumptions built in there, like, I'm not in a matrix.
Right.
But we're
simplifying for
that's
the
right.
sake of
That's
this
right.
example.
But we directly observe that it's raining. That's what he says here, right? So you directly observe that it's raining, and this observation naturally enough causes you to form the belief that it's raining. And then you get to his office, and you're soaking wet, right? Now, he says his office doesn't have any windows. Right now, he says he doesn't. It's not a cubicle, but it just doesn't have any windows, right? And so he says. So what can he make about the idea? What can he infer from the observation that you are soaking wet in his office?
Right. Well, you walked through the grass and the sprinklers came on.
Yeah, right. So that could be an inference from what you're doing. But he says, you come into my office soaking wet, and though my office has no windows, I too form the belief that it's raining. Notice he says my belief is formed very differently from yours. You directly observed that it's raining. He infers from the observation that you're soaking wet that it's raining, right? So one is a direct observation, the other is an inference, an inferred kind of belief.
Right. That's why it would be hard to prove, quote unquote, evolution, because you're seeing a species. Let's assume, for the sake of argument, that evolution is true. You're seeing species come up with new information within its DNA structure. Hopefully we can observe that to a point in time which a new kind is made out of that new information. And you don't ever really see that because of the long expanses of time that it takes for the speciation to come up with a new genus or kind or whatever label that you want to put on it. So you don't actually see evolution in action. You might see microevolution, which is different than macroevolution, a change in kind rather than a change in species, or adaptation is what we would pretty much call it everywhere else. So the observation is, here's a new animal, here's a new organism. It takes a long time, and you could never observe evolution, capital E, evolution, in action.
Right, yeah.
You have to infer that.
Good. And so he gives us another example, which he says is probably the most important scientific, philosophical, and religious debate in history, right? And that's the 17th century debate over the geocentricity and the heliocentricity with regard to our solar system.
This was big news back then.
That's right. It was a big debate. It was a big argument, right? On one side were the Copernicans, right, that says, hey, look, the sun is the center of the solar system, right? Heliocentricity. On the other side were the Ptolemies or the Aristotelians that says, no, the Earth is the center of our solar system, right? Geocentricity, right? And so he says, now it's important here that the debate was not about, notice, observation.
Yeah, very important here.
Yeah, right? Everyone generally agreed that the sun is over there at some point, at some time, and then the sun is over there at some other time, right? Everybody agreed with the observations.
Everyone sees it, sure.
Yeah, right? So the debate was over how to explain the appearances of what was going on that everybody observed. Right? And so the debate, he says, was about theory. That's the explanation of our observations, the explanation of the phenomena that's being observed, right? He says, obviously, we don't observe heliocentricity or geocentricity, right?
Unless you got further outside and are able to establish where the center of anything was in the universe.
So those theories, he says, are inferred stories about what goes on behind the appearances that we have. So so in the Copernican debate, each side had a possible answer to the question. Here's the question. What does the sun, or why does the sun move the way it does in the sky? Why does it move the way it does in the sky? Well, one side says because the Earth, so geocentricity, the Earth is spinning and rotating around the sun, right? It's spinning on its axis and rotating around the sun, spinning approximately every 24 hours and rotating roughly every 365 days. And that then is the explanation for why we see the sun here at one point and over here at another point.
Mm-hmm.
The other side says, no, the sun is moving around the earth, right? And that's the explanation, right?
Right, and it's not just apparent. Like, a good history of philosophy or philosophy of science class will kind of bring you into the fold of exactly how long this took. Like this Copernican revolution was over a long period of time,
several hundred years,
and really the thing that kind of caused issue was planets kind of doubling back on itself, and there's no explanation for that within a certain theory or a certain model.
Well, and oftentimes, and he doesn't get into this, but oftentimes technology allows us to help end some of these debates, right? So the telescope, the newly invented telescope, then allowed, for instance, the observation that, lo and behold, Jupiter had satellites going around it. So not everything then is circling around the Earth. And so that was the evidence, used as evidence, right, to show that something else is going on. But anyway, he says an explanation then is often an answer to why questions, right? Why do things appear this way? So a theory then is an explanation. It's an explanation about why. The type of inference leading to each theory, we can call this inference to the best explanation, he says, is a complicated as it is common. And so he wants us to understand this particular complicated process of how we come up with theories, how we test theories, and all the real hard work that it takes up, what science is all about. So he says science then is in the business of inferring theories, and scientific theories must agree with observations, right? Past, present, and future. These theories must make contact with the world, but no matter how well a theory predicts or represents observable phenomena, no matter how well it's supported by this agreement with observation, it's still a theory simply because it's not observed, it is inferred, right? We infer it. We look at the guy standing in the office soaking wet and we say, it must be raining outside. Now, as you mentioned, there are other theories, right, about what might have caused him, right? He walked through, the sprinkler suddenly came on while he was walking
There's
by.
a prankster who's got the old bucket over the doorway.
The doorway, all kinds of things, right? So those are various theories, we might even say, in what he's going to talk to us about, hypotheses, right? Are theories, but they're inferred. We didn't observe the bucket, right? And we didn't observe the sprinkler, and we didn't observe the rain. We're making an inference based on what we do observe.
Even if you have that person say, I was rained on, you have to still infer it because you're inferring, is this person trustworthy? Is this person mistaken?
Yeah.
Is this person of sound mind?
Yeah, good. So there's basically three ways then that we do this in terms of coming up with beliefs. There's observations that kind of force our beliefs, right? Right? I mean, it is raining, right? Yeah, theoretically. Yeah. There's inference, right? Oh, it must be raining because, he's soaking wet in my office. And then there's testimony. That's what you just said, right? He told me that it's raining outside. So those are at least three ways that, we kind of...
He would not like our testimony.
Yeah, he wouldn't like that one, right. All right, so...
Testimony is also how we sneak in God into our worldview there, too.
So the real question, he says, is this: how good are our reasons for believing theories, right? How good are our inferences, right? That's what he wants to examine, right? So a theory then is this as an explanation. It's an attempt to answer these why questions. Right. And so now he wants us to examine how good are these reasons for believing a particular theory? How good are the inferences that we make with regard to these questions, right? All right, so next he moves to hypothesis. Right.
Hypothesis is simply an unobserved explanation. Take a standard gloss of scientific methods. So you have the observation, you see the sun move, then you have the hypothesis. Oh, well, clearly we're at the center because it's moving around us. That's what I see. Prediction, I have a prediction that there'll be other bodies in the sky that moves around us. there's an experiment. I look up, I see the moon. Hey, the moon's moving around us too. Look at that. My theory is proven until something else happens. So again, this is kind of a low-key version of what the scientific method is, and we'll cover a bit more of that.
He calls it a G-rated version, right?
Yeah, it's more messy than that.
Yeah.
So we come up with a theory that makes sense of the facts that the world behaves this way. So our hypotheses for are really just theories. One of the main ways we decide which ones are better than others is by comparing how well they predict the world's behavior. So if we go back to our geocentric universe, I see the sun go that way. I predict if my hypothesis, my theory is true that we're at the center of the universe, then I'll see other bodies move around me. Well, there's the stars, they move around me. There's the planets, they move around me. The moon moves around me. I can even throw something up in low atmosphere and it keeps going around me. I am clearly the center of the universe.
That's right.
So.
Okay. And don't forget it.
Yeah, exactly. and so how do we come up with these predictive behaviors? Well, we do it by experimenting. We look at things, we test things, whatever our observation is. We want to find similar areas where we can have an experimentation where we're reproducing something, or we're checking our theory or hypothesis to see if we can expand the explanation power of that.
Yeah, and the idea of explanation here has to do with we make a the idea of testing a theory is we make a prediction and then we see how well what we predicted to happen, how well that happens.
You essentially want to try and destroy it. You want to throw everything in the kitchen sink at it.
Well, that's one way, right? I think Karl Popper, was the philosopher of science. Karl Popper said that's what scientists really do. They're not trying to come up with theories; they're trying to defeat theories, right? Yeah. And so, that's one way to look at what scientists are trying to do, right?
Or there are people, and I forget the really good book. It was Einstein versus Bohr about the formation of the atom, right?
Right.
And man.
Well, it was quantum theory in general.
And they were so key. Like,
in fact, he's gonna talk about that briefly here. Yeah.
I mean, both sides were just vehemently opposed to each other until all the theories, explanations stacked up, all the evidence stacked up, and the Bohr side was throwing up their hands and it's got to be this way, but we don't like it.
Yeah, actually Einstein spent most of the rest of his life trying to figure out how that all worked, right? and couldn't come up with a way to explain that. So he says explanation is of a specific kind, the unobserved kind, right? That's the idea. So hypotheses and theories are basically the same thing. Theories is more broadly many hypotheses, right, to help us to explain, and then a hypothesis is a narrow version,
right? So
of the theory.
Geocentrism would be a theory. Things move around me, or things move in relationship to me or the Earth would kind of be a more specific hypothesis.
Right. So they're really the same thing, just in many theories, is what he calls a mini MI.
Micro versus macro evolution of theories.
Yeah.
And so throughout all this, we have to remember that what we're ultimately after is that scientists tell us, or even hints, that God's existence is unlikely, whether naturalism is most likely true. So
right. So, and he's going to come back to that, right?
Yeah.
But so he wants to help us to focus. That's the main thing that he's getting at here. But he's trying to help us to see how hard science really is and how difficult this particular claim can be had to hold. Right?
We know God doesn't exist, and we also know. So that's the negation of something. We also know that naturalism is the only true and proper path
for science,
the narrow path.
That's right.
Yeah, not the wide path.
Right. All right, and so so he says we'll turn next to an important fact that the relationship between observation and theories, after which we'll look at the requirements for a successful scientific theory. So what is the relationship between observation and theories? To construct a scientific theory, he tells us, and he also says this is also sometimes called a model. right?
Mhm.
We first carefully consider our observations and then tell a plausible story that might explain the observations, right? That's how we construct a theory, right? And even the considered gap, though, there's a gap here between separating observations from theory that can make arriving at a decent theory an ordeal,
Mhm.
right? And even once we've constructed a theory, we can never observe that it's correct, right? So one major complication in all of this is that there's usually more than, and here's one of the issues now, there's more than one theory or hypothesis that will match the observations, as we just saw with the Copernicus Ptolemaic debate, right? There's more than one theory that can match all of the observations that we have.
And
right?
it's not just those two. There can be also other ones. So the matrix can also be in that group.
good,
But it's
yeah.
there's no center of the universe because there's no universe.
Yeah. So this is called, and he labels it here, empirical adequate, right? Empirically adequate. In other words, our sense perceptions, our empirical observations are adequate for both or several theories, right? All our observations can fit any of these various theories. So each theory is empirically adequate. Our sense perceptions can fit all of the various theories, right? So he says, in such cases, the observations alone then can't settle the disagreement, right? Sun is over here, the sun is over there. Sun is over here at one time, the sun is over there at one time. So how does that settle whether or not the sun is moving around the earth or the earth is spinning? Well, it doesn't,
Yeah.
right?
Which
Both theories are empirically adequate
Right.
to the observations that we make.
and logically sound. too.
Yes.
So when we go back to Hume's fork, we both have observations that are the same, that are agreed upon, and we both have the same laws of logic that are the same. So how do we come up with information?
Yeah, right. So that's the issue. He says, so experience alone can't adjudicate between equally empirical adequate theories, right? Excuse me. Now, again, he's throwing a lot of terms, highfalutin sounding terms here at us. But the basic idea here is our sense experience, our observations, what we observed, right, can't adequately judge between the various theories because both of the theories fit our observation, right?
So there's got to be other criteria that we can come
Right.
up.
So other criteria have to play. So, for instance, simplicity, right, which is the simpler theory.
Yeah.
Right.
Old Occam's razor.
Yeah.
Limited imagination, Occam's razor. Yeah.
Ontological and conceptual economy, aesthetic considerations, suggestive mathematical symbolism, how well a theory fits with the rest of what we believe about the world. All these types of things are in a host, he says, of hard to characterize factors. So we look at, and oftentimes these are called empirical empirical values that we attach to a particular theory. So the simplest theory then is more likely to be the best theory, something like that. Right?
Like if you look at Newton, he still held to the theory of the spheres in the universe, and it really was a huge revolution to think that elliptical orbits were something that were out there, or that, I mean, just throwing off the shackles of geocentrism. I mean, you almost had that for all of human history.
So Aristotle had taught that perfection in circles. So it had to be a perfect circle. That's why they were in the heavens, because where the perfection lies, and so everything revolved in perfect circles. And so this egg-shaped kind of circle wasn't even thought of.
Yeah, good old Kepler came along and saved us with that.
So it says the point now is that there can be more than one possible theory that empirically matches a set of observations. That is, there can be more than one theory that our senses perceive, that's empirically, right, matches the observations. And philosophers of science call this that the observations underdetermine the theory. Right? The observations do not allow us to determine which theory is the correct theory. So we call that the underdetermination of theory by observation. right? That's under determination, another kind of highfalutin. Yeah. Observations alone, which is where the theoretical rubber meets the empirical road, he tells us, cannot fully determine or nail down a unique theory. Indeed, one philosopher, Quine, famously said there are an infinitely number of empirically adequate theories for any given set of observations, right?
Especially if you're Hawkins or Krauss, who has an infinite number of universes.
So there are an infinite number of...
even more.
Yeah. Of course, he says some will be more plausible than others, right? I mean, space aliens might be, right, dumped water on me, and that's why I'm wet, and it's not raining, right? But, plausibility, by the way, has to do with, again, the way we believe the world is, our background information, background knowledge, and, how what we think could or could not happen. He gives us an analogy here, right, of this XY graph.
So we have this theory, and it's pressure and temperature. They're somehow related. And we have a theory that if they're related, we can come up with a mathematical formulation or relationship that pressure and temperature seem to have. And so there's a lot of different ways in which we can plot this graph. We can draw a straight line from one point to the next, or we can kind of do this weird old zigzag to get to every other point along the way to our 2 points that we're drawing a conclusion from. And so to believe that the temperature and pressure have anything to do with each other is a factor in deciding. I mean, that's a theory. We don't observe those things. We just kind of assume that they have a correlation between them, and it could be complex. It could be simple. We don't really know, and so there are an infinite number of ways that we can connect these points, and the data alone cannot make the decision for you. You'll need additional temperature, pressure data, or some other criteria, or both.
Right.
So it's not as simple as you have this, and you just draw, your
so
mathematical
the simplest
equation.
explanation is a straight line, but that may not be how these things are connected, right? So you have one data point, so you have your XY axis here, you have one data point here, you have one data point there. Well, I guess this is the way it works. Well, no, not necessarily. It could be all kinds of things going on.
Logarithmic. It could be.
You can have squiggly lines all over the place that finally meet that.
Could dip down into negative X territory. You never know.
Yeah. Right. So, of course, what he points out that that these things are even connected is kind of curious. We make that assumption that we can connect these things mathematically.
Yep.
That's an assumption that we make, may or may not be the case. Right.
I always have to do this one because it's always my favorite, because it was a good little meme online. Is that back in the day you had more pirates and less climate change. Today we have less pirates and more climate change. Therefore, there's a correlation of some factor between pirates and climate change. So all we need to do is increase the number of pirates. We lower the climate.
Ooh, wow.
Straight line.
Brilliant theory, right? Yeah, based on the data that we observe.
I'm going to be a member of Congress in no time.
And the Nobel Prize, right?
Yes. Well, so Sweden has a pirate party, so I could just as likely join them.
Yeah, good. All right, so so there's lots of theories is the idea here. Lots of models to choose from. There's lots of ways to explain the data, that explain our observations and that sort of thing. And that's the point that he's making here. And so the observations are underdetermined, right? They underdetermine the theories. There's lots of ways to explain it. So one theory is, one could say, you have multiple theories based on various observations, and it's pretty difficult to choose. All right, so now what he wants to do is to go back to this this idea of inference to the best explanation. He says, when constructing a theory, we have to sift through all the possible explanations, right? Because there's a bunch of them, right? looking for the best one. That's what we want, the best explanation.
Again, going back to you're staying in his office wet. How many ways can you get wet? You could have stepped into a shower. You could have been rained on. Space aliens. You could have walked through the field with the sprinklers. You could have had the prankster pour something on you. You could have tripped and fallen in the janitor's mop bucket.
Yeah.
I mean, there's a water main break. All those factors come into effect where you're trying to figure out what the best explanation
of the observation that you're making, right? And so we want, and this is called what he calls, and what is generally called, inference to the best explanation, right? Although it's not clear exactly what kind of inference it is, technically speaking, he says. So in any case, inference to the best explanation, though, isn't unique to science, right? And he gives us now several examples and illustration of inference to the best explanation. The first one is Sherlock Holmes. Right? Sherlock Holmes does it every time he solves a case. He gathers facts during his investigation and then arrives at the best explanation of those facts. Hypothesis, he says, that answers why are things this way. That's the explanation. That's the hypothesis. The answer being, because Moriarty is the killer. Right. That's the best explanation.
Or let's take this out fiction. Any trial that you come in contact with is not based on facts as brute facts, but are inferences from those facts.
Right.
And it's people trying to prove why is the body on the ground? Because the husband's the killer.
Yeah.
Yes, of course. And again, it's always the husband.
Good. Yeah. So it's interesting he uses Sherlock Holmes here. Usually, when you read Arthur Conan Doyle on Sherlock Holmes, he, I think, describes what's going on. He calls Sherlock Holmes doing deduction.
Yeah.
And really this is induction, kind of, right? Sherlock Holmes isn't making necessarily a deductive case. He's inferring inductively, probably, right? He doesn't say necessarily Moriarty is the killer, but probably. So that's an inductive one. But anyway, we don't want to get more technical.
Yeah, when he meets Watson, he says, "Oh, you're right-handed because you wear your watch on, your left wrist."
Right.
But maybe that's just a preference that Watson does, or because of his time in the war, he needs it on that wrist in order to do
his
pulse.
Gun right, or whatever. Right. Yeah. So it's a probability statement, not a necessity statement.
But he's Sherlock Holmes, and he's got a hidden author in his back pocket, so he's always right.
So that's Sherlock Holmes. Here's another one. A more mundane but oh so much important example is when your doctor tells you that you have a staph infection, right? She sees the redness and swelling, feels that the skin's temperature is higher than normal, hears your complaint about fatigue, etc. Now notice she never observes that you have a staph infection. These same symptoms, could be cantankerous lupus, right? But she thinks that staph, is a better explanation given everything that she knows, right?
Because you can actually treat staph, so it's better to assume that than lupus.
Right. So based on the doctor's observation, the theory, the best explanation is a staph infection.
Because staph infections are more prevalent to occur. There are maybe other signs that lupus brings about that you don't have, and so when you're pointing your arrow at the target, you have to know at least to point it at a target. So you're not going to take these things and say there's a whale on your foot.
Right.
Possible explanation of something, but. Staph infection for the doctor is probably where it's coming.
The last one that he uses, and I'm picking these out because he's going to refer to them later. He says, one last example. You are an astronomer in the early 1800s and notice that the planet Uranus is now not following the path predicted by the current astronomical theory. Right? You made the calculations yourself. The planet's orbit is ever so slightly off where it should be. There are various possible explanations. You realize perhaps you calculated the orbit incorrectly or made careless observations, or perhaps current theory about planetary orbit is just plain wrong. But after much toil and trouble, you arrive at another hypothesis or theory. perhaps there's an unseen planet affecting Uranus's orbit, right? And after painstaking research, you find that there is indeed another planet exactly where you calculated it should be. You call it Neptune, and check. Discover new planet off your bucket list, right? And so notice here is a situation where the theory that you had seems to be wrong, and he's going to make this point later, right? But you don't give up the theory. You do further research, and you find out that indeed the planet isn't doing exactly what it's supposed to do. There's another planet affecting the orbit of that planet.
Right. And going back to what he first said, when you have science and you have the beginning of science, we didn't have this knowledge, and boom, all of a sudden we have technological advances, or, hey, look, we proved that there's another planet in our universe until scientists get together and call Neptune not a planet next.
Yeah, like they did with Pluto.
Right.
Yeah.
But you have this big, giant discovery, and so science gets to kind of whitewash all the critiquing of and struggle that you did to arrive at that, because, yes, you could have picked, my measurements were off.
Right.
The way that planets travel must be the issue at stake.
Yeah, that is Newton's theory is wrong.
The angels are pulling this planet back just a little bit in order to convey some message to someone that's not me.
Right.
That's a possible explanation.
Right.
Oh, nope, I've come up with this theory. I've done some calculations. They seem naturalistic to people, and boom, I found Neptune. And so you can't argue with the results. Look, I did science. No, you had a theory that worked out.
Right.
And so when we go back to photoshopped science, that's what it is this guy in a lab coat makes this prediction, and of course, it's got to be another planet. We have to know this. Well, no, it didn't have to be that.
Right.
But it just happened to be that. And so you get to kind of claim the snapshots of the beginning.
Look what science has done
end.
for us.
Mm-hmm.
Yeah, look at how this happened, and look how easy it seemed. And this point here is it ain't that easy.
Right. Science is really hard.
Yeah. Good. Well, let's leave it there, and we'll pick up the rest of this chapter next time, and again, plow through this idea that real science is hard. Mm-hmm. He's going to show us some other ways that science is hard.
Some of our favorite topics, like worldview and how that affects everything.
Yeah.
So join us next week, and we'll continue covering why real science is hard, so that we can be very good atheists.
We'll see you next time.